So I will be presenting about ChorCaml. So it is the first embedded domain-specific language written in OCaml for choreographic programming. The goal of it is making distributed programming easier for the programmer and less error-prone. Here at the bottom, you see a quick sneak peek at the bookseller protocol implemented using ChorCaml. I will explain it in detail a bit later. So first of all, what is choreographic programming? It is a paradigm for writing distributed programs. And unlike in naive approaches, instead of writing a separate program for each participant, the programmer writes one big unified program known as the choreography. One of the restrictions of choreographic programming is that all participants need to be known at compilation time. And furthermore, choreographies are defined over an arbitrary communication backend that uses message passing. Sorry, just a second. I messed up my presentation again. Okay, sorry, should be fine now. So, and it is often convenient to define choreographic languages as an extension of some base language, which provides local expressions, and the choreographic part simply augments the type system with locations to represent participants and provides safe communication operations. This in mind, let's have a closer look at how this might look like in practice. And for this purpose, I will present the bookseller protocol. In this protocol, we have two participants, a buyer and a seller. The buyer wants to buy a book from the seller if it is within their budget, and if that is the case, they want to get a delivery date back from them. A naive approach of writing this would be implementing two separate programs which communicate between each other using send and receive primitives. On the left-hand side, you see the buyer program, and on the right, the seller program is present. So using this approach, the programmer has all the responsibility for correctly matching up the send and receive operations. In case of a mismatch, severe errors occur which become visible over time and are usually unrecoverable. And this is largely not ideal, and that is what choreographic programming attempts to solve. So this is a pseudocode example of what a choreographic program for the bookseller protocol could look like. As you see, the main difference is that the two programs are now joined just into one piece of code. We make use of the which in this case, that being the variable t at location buyer. Lastly, we have choreography level branching. It is interesting because it performs some implicit synchronization between the participants. The conditional is located solely within the buyer, who makes the decision whether the price was within their budget. And based on that, the respective participants of the choreography are informed of it automatically, so they can proceed as expected. In this case, if the decision to buy the book was made, the seller would send back the delivery date, and otherwise, the program just terminates returning none. Now, to execute this program, you would need to make use of the compilation technique known as endpoint projection. At its core, this is a technique that takes the original program, a location for which to compile, and then it produces executable code just for that location. In the previous example, we would call endpoint projection once with a buyer program and once with a seller program to end up with two separate executable programs. And those programs could be executed in parallel, and they would communicate correctly. With this approach, the programmer does not have to manually write the send and receive operations and try to match them correctly, but they can simply trust the compiler to do the right thing under the surface. Now, with this background, where does ChorCaml stand? First of all, it is an interpreted language. It is embedded as a domain-specific language within OCaml. Provides a functional interface using the FreeR monad and offers high levels of modularity. This allows the use of a variety of communication backends and interpreters for the programs written in ChorCaml. And the main one being the TCP backend included with the implementation. I should mention that this project was largely inspired by Haskell, which, as you might have guessed, is a Haskell library for choreographic programming. Now, let's take a closer look at the implementation of ChorCaml. The first point is the representation of values. The representation of locations. This concept needs to be unique on the type level to ensure safety. But since we're using an interpreted approach, we also need to distinguish between locations at runtime. So they need to be unique on the value level as well. For which reason I chose the representation shown in the lock_s module. It takes a type and a UID integer used during runtime. Then for convenience, we wrap it in a type alpha lock mod, where alpha is the type unique to that specific location. And lastly, we have an example of creating an instance of this location module. This is slightly clunky, but it can easily be extracted into a PPX to perform most of these actions. So first, we would define a new type, Alice lock. Then we would create an appropriate module of the lock_s signature by passing Alice lock as the appropriate type and providing some unique ID. And lastly, we wrap this module into a value for convenient use later. Now, with the location representation sorted out, we can take a look at program value representation. So program values are effectively arbitrary OCaml values paired with a location module. This is represented in the lockval data type. It is now, the one unusual thing to note here is that an empty clause is also provided. This is, once again, because we have taken an interpreted approach. And occasionally, our interpreter will be processing expressions which are not intended for the location that is currently being interpreted. In that case, we need to skip the expression, and then we simply return an empty value to indicate that this was skipped. Now, it might be slightly alarming that the unwrapped value would fail in the empty case. However, the rest of the language definition and all the data types involved in it are structured correctly in a way that ensures that the type system would catch cases where we're trying to unwrap an empty value. This similar approach was also taken in Haskell. Next, we can move on to the choreographic primitives. The primitive expressions of choreographies. And this is highlighted in the following data type. The three main cases to note are, first of all, var. This case of the GADT takes a location module, an arbitrary OCaml value, and uses that to create a located value. Next, we have app, which takes a located function, a located value, and uses them to create an appropriate value of the same location, which is the result of function application. And lastly, we have the com primitive, which takes a location module and a located value. And the result of it is the same value located at the destination module. This is the expression that gets converted to send and receive primitives by the interpreter. Additionally, I have omitted this here, but we have a branching primitive as well. It serves just for convenience and can be implemented using the other primitives already. Next, to facilitate the implementation, I made use of the freer monad data structure. In essence, this is a highly versatile type that simply represents arbitrary type-aligned chained expressions. And it is defined abstractly over a box module, which in our case will be the base choreo type I provided before. And the freer consists of two cases of this variant type. Pure just signifies the end of expression sequence, and impure can be seen as the head of an impure contains the head expression followed by a continuation that returns the remainder freer monad. This is once again highlighted in the bind operator implementation for the freer monad. And later in the presentation, I'll be using the binding operator syntax instead of the bind operator itself. And as I mentioned, we use our base choreo type to instantiate the freer monad, and that creates the choreo module, which provides all the main utility functions for writing choreographies. Now, just before I jump into some usage examples, I also implemented a couple of convenience operators. So the user doesn't have to work directly by using the variant constructors. So the first operator to note here corresponds to var. It just takes an arbitrary OCaml value x and the location module loc to create a located value. Next, we have two operators for communication. They do effectively the same job, except one of them first lifts the given value to the choreo monad, and the other one just passes the values to the communication primitive immediately. And lastly, we have two more operators which correspond to the app primitive. Once again, one of them performs a lift before doing the rest of the logic. And I should note one thing. Some of you might have noticed that lockval roughly forms an applicative. This is sort of highlighted in these two operators, which more or less correspond to the main two applicative operators. However, the type signature doesn't match perfectly because we're wrapping the result into a choreo monad, and therefore I chose slightly different characters to represent these two operators. Now, we can come back to the bookseller protocol implementation in ChorCaml. This is the same protocol as highlighted before, and what's happening here is that we're sending the title value over to the seller, which produces the located value t, which is located at the seller. Next, we're using the caret operator to call getPrice on the title at the seller location, and then we're using the arrow operator to send it over to the buyer, which together results in the value p located at the buyer, containing the price of the book. And next, the buyer performs the decision locally. This happens once again by using the caret operator, and here we just have a curried version of the comparison operator that's pre-applied with the budget constant, and then compared to the price p. This results in a Boolean decision located at the buyer. And next, we're using the branch function, which is somewhat self-explanatory. Based on the Boolean value located at the buyer, it performs either the first branch, the true branch, or the false branch. The latter case just returns a none value at the buyer, while the former case performs some more logic to get the delivery date out of the seller to the buyer, and then simply wraps it in an optional value. Now, once we have a choreography like this, the library provides two main ways to execute it. The first one is local execution, and it is trivial in that it simply runs the program in a non-distributed fashion in a sequential way, and that is simply useful for debugging purposes. And then we have the second interpreter, using the aforementioned TCP backend. In this case, we pass the bookseller choreography, a certain TCP config, and the location for which we're executing the program. And this uses LWT internally for asynchrony. So we pass it to LWT main run to actually execute it. And for the bookseller protocol, if we had two instances of this running, one with buyer and one with seller, we would have a successful communication between them, producing either a delivery date at the buyer or just nothing if the buyer decided not to buy the book. Yeah, that more or less sums it up. I have also included a slightly more extensive example of a choreography using ChorCaml. Here we have the three-phase commit protocol, where Alice and Bob participants communicate between each other with the help of a coordinator, and based on their results, they either commit their votes or don't. Yeah, I have also included an example of the same three-phase commit protocol in Haskell. It is a bit more verbose, and one of the things that ChorCaml tried to improve was the verbosity of the unwrap operations, very, very frequently present in Haskell. Yeah, thank you for your attention, and I'm happy to take any questions now.
I have a question on upgrading Haskell programs. So obviously you have this maybe running on different systems. Does the upgrade need to be atomic with all participating programs at once, or is there some kind of support for versioning possible in the communication protocol?
Mm-hmm. Yeah, unfortunately, there is no support for convenient upgrades. The programs should be compiled from the same exact source code at the same time.
Thank you.
So thank the speaker again.
Yep, thank you.